Hey everyone. So I'll be talking about my upcoming work, which is titled Towards the Space-Time Derivation of Quantum Extremality. And this work is done in collaboration with Onkar Pardikar. So let's get started. So in recent years, there has been incredible progress towards understanding the emergence of space-time geometry from entanglement and holographic conformal field theories. And the first of these results is the famous Shri-Takayama formula, which instructs us how to compute the entanglement entropy for boundary subregion R in terms of the area of a bulk extremal surface anchored at the boundaries of R. However, it is well known that the RT formula is only an approximation that is valid to leading order in G Newton. It was conjectured by Engelhardt and Wall that the correct prescription is to extremize the full generalized entropy function. And the resulting surface is called the quantum extremal surface, and the entanglement entropy of the boundary subregion R is given by evaluating the full generalized entropy in the bulk across the quantum extremal surface. So a key step towards proving the RT formula was taken by Liakowitz and Maldacena, where they developed the holographic replica trick. And one can also prove the quantum extremality formula using similar methods, but all of these methods are manifestly Euclidean in nature. So recently, a version of the quantum extremality formula called the island formula was used for a partial resolution of the black hole information problem. However, the microscopic origin of this prescription remains mysterious. We believe that a Hilbert space interpretation of the quantum extremality prescription would be a crucial step towards understanding the entirety of black hole evaporation. And towards that end, in this paper, we initiate the study of quantum extremality from a Lorentzian point of view. So in this paper, we don't talk about black holes. We simplify the problem considerably by considering small fluctuations around vacuum areas. This is achieved by considering a one-parameter family of Euclidean path integral states on top of the vacuum sourced by a double trace operator in the boundary. Here O2 is the double trace operator, and this corresponds to a one-parameter family of dual bulk geometries GAB and state psi, both of which are functions of lambda. And we choose the boundary subregion to be the right half space, which is dual to the area Strindler wedge, and throughout this paper we consistently work to leading order in lambda and G Newton. So the reason we choose our boundary state deformation to be a double trace operator is shown in this cartoon picture here. So double trace operator insertion in the boundary sources gravitons in the bulk at order lambda. And since our calculation is inherently perturbative in lambda, this greatly simplifies our lives. So the boundary state perturbation displaces the location of the extremal surface because of the bulk metric and state fluctuations. And this displacement is parameterized by some vector field, let's say V. By solving the variational equation furnished by the quantum extremality prescription, we can solve for V in terms of the metric fluctuation in the Lorentzian geometry. The formula for V is given here. We then show how to compute this formula, derive this formula for the displacement profile of the QES from a first principles ADS CFT calculation. And the rest of the calculation proceeds by computing the relative entropy between the state psi lambda and the CFT vacuum in two different ways. We first derive a gravitational formula for the relative entropy using the Lashkari-Van Ramstorm formalism, and this prescription is essentially a corollary of the quantum extremality prescription. And then we perform a first principle computation of the relative entropy using the standard formula given below. And the main novelty in this analysis is that the computation of the double trace two-point function is performed in a particular time-folded geometry reminiscent of the gravitational Schwinger-Keldysh formalism. And then demanding that these two computations match up lets us recover the formula for the displacement profile of the extremal surface as prescribed by the QES formula. So in this sense, our analysis serves as a consistency check of the quantum extremality prescription without relying on Euclidean methods. We have also derived a formula for the displacement profile of the QES that is valid non-perturbatively in lambda. And this formula is essentially a corollary of the fundamental result of Sheehan and Faulkner, which relates the shape derivative of the relative entropy with the average null energy operator in the bulk. Since our analysis is perturbative, we make no attempt to prove this more general formula in this paper. However, several fascinating questions remain. So how does one formulate a clean non-perturbative picture which lets us derive the all orders formula described above? So what role does quantum error correction play in all of this? What is the correct way to generalize this analysis to black hole spacetimes? And if one successfully manages to do all of the above, then can one naturally land up on the island prescription? So all of these are fascinating questions for the future, which we encourage the audience to think about. But that's all I have to say for now. Thanks for listening.